Okay, so we shall continue with the topic of cryptographic hash functions, which we started last day. So we were essentially discussing about the relative order of hardness of security criteria for hash functions. So we will continue with that, and then discuss about a particular type of construction which is very much popular. It's called the Merkle-Damgard construction, and it is also it is an iterated construction technique for hash functions. Okay, so we will discuss about these topics. So to start with, we have discussed about these two reductions. We are discussing about these two reductions. We are discussing about the collision to second preimage problem, so that we discussed last day, and we will be discussing about the collision to preimage problem. Okay, so one thing actually that we were considering these type of reductions, and there were some queries like why do we put this if, right? So one reason is because this is also a probabilistic algorithm, right? So therefore this doesn't always give you the answer. So it gives you the answer sometimes, it does not give you the answer sometimes. So therefore, for example, this is a La-Vega algorithm, La-Vega randomized algorithm. So therefore this can fail also, right? So when this algorithm fails, then this collision to second preimage also fails, right? So therefore this if is only to check whether this actually gives you a answer or not. Therefore that means that in case of a La-Vega algorithm, whether it terminates or not. Okay, and there is a probability of it terminating, and that probability is denoted by epsilon. So if that is the probability, then the probability with which this collision to second preimage also gives you a correct answer is also epsilon. Okay, and that is the precise reason why this if was kept actually. But again, as we discussed in the last day's class, we do not require to check for x and x dash being equal or not, because since this is correctly giving an answer for the second preimage problem, therefore this is automatically taken care of. Okay, so this is something that we have discussed, and we are discussing about this particular reduction. So therefore this is a collision to preimage problem. So we know that preimage problem means given hx, we have to return an x value for which the hash value are the same, right? That is the preimage problem. So we assume that there is a solution to this preimage problem, and from there we show that in that case we can also solve the collision, we can also solve the collision problem. Okay, so therefore if this is the question, that is if you are choosing x at random, uniformly at random, and then you compute the hash value, that is hx value, and then engage the algorithm for computing the preimage. So therefore this is an oracle to which you are asking a question. Okay, and it gives you back an x dash. So one thing you have to now check is whether x and x dash are same or not, right? Because this just gives you the preimage. So therefore you do this check, that is whether x dash and x are same or not. If they are not same, then you can return x comma x dash, because both of them have the same hash value, and they are also not equal, right? So therefore this is a solution to your collision problem as well, right? So now the question is that what is that if I assume that the oracle preimage is a 1 comma q La-Vega algorithm. So that means 1 comma q means the probability of giving you the preimage solution is actually 1, and there are q queries required. Then what is the corresponding epsilon value and number of queries required for this collision to preimage oracle? Okay, so number of queries, you can easily see that if this query is q, and since there is an extra query, it's q plus 1. Okay, and about the probability, we will make an assumption. So the assumption is as follows, that is the cardinality of x is twice greater than the cardinality of y. Then we can show that you have actually the probability of half comma q plus 1. Okay, so in order to understand that, let us consider a proof. So the proof works as like this. So consider the space. Okay, so consider the space of x. Okay, so now what we start doing is that we start partitioning this space. So we start inducing partitions. So you know that we can induce partitions by equivalence relations, right? So therefore we can start inducing partitions. We start partitioning this set such that all the values which lies in one partition, they have got the same hash value. Okay, so that means that if there are two values like x1 and x2 which is one partition, then h of x1 and h of x2 are the same. Okay, so that is the definition of a partition. Okay, in this case. So now consider that So therefore now let us consider that suppose how many such partitions are there. So therefore the number of partitions which will be there, so I call them, suppose all of them are some collections, okay. So therefore suppose this is one C1, this is C2, this is C3 and so on, then the number of such collections will be equal to the cardinality of y, because all of the partitions are indicating one particular hash value. So therefore the number of collections is actually equal to the cardinality of y, okay. So now let us consider that suppose there is a given value of x. So suppose you have been provided with an x value, what is the probability of success with which you are actually solving the collision problem? So your probability of success will be actually equal to, so how many total number of, so given x, how many total values are there? So there are actually, if I call this as the equivalence class, so there is basically one partition if I indicate by this symbol, then the cardinality of this is the total number of possible values which I can choose from, right. Among them except one, all of them are my correct values, because one will be the same value, right. So do you understand what I am saying? So suppose let us consider one particular partition, okay. So suppose you are considering this partition, okay, and suppose x lies in this partition. So in that case, when you are asking the preimage to give you a result, the preimage is giving you a result with a probability of 1. The preimage oracle, we have assumed that it is a Lavegue algorithm with probability 1, right. So therefore it will definitely solve the preimage problem and it will return you some value, right. So what are the possible values which it can return? It can return the number of values which are lying in this partition, right. And what is that set? So I indicate the number by equivalence of x and the cardinality of that, right. So apart from, in that, except for the number x itself or the value x itself, all are correct values for the collision problem, right. So therefore your probability of success, if you are given this value of x, is this. Any doubts? So now we need to consider the average case probability, right. So therefore what we will do, if I am interested in the average probability, then what I will do is that I will take it over the entire set, right. So therefore I will do a sigma operation of this, and I will vary the x over the entire set x, right. So this we can actually write in this fashion. I can, first of all, so there are so many collections, right. So let us break this sigma into two sigmas, and in this particular sigma, let us concentrate that x is belonging to one particular collection, okay, and here the collection belongs to all possible collection sets, okay. So let C be the collection set which is comprising of, say, C1, C2 and so on. So how many total collections are there? C cardinality of y, right. So therefore consider that this is your total collection set, and therefore you know that this is how what you are doing, right. So therefore what does this value compute to? This is the number of elements in the corresponding collection C, and therefore this is also cardinality of C minus 1, right. So therefore this will compute to now 1 by cardinality of x, and this, if I keep this sigma, so this will be for all the values of x which lies in cardinality of C. So how many values are there? There are cardinality of C values, and this value is a constant. So you get cardinality of C minus 1, right, and this computes to therefore 1 by x. I can break this into cardinality of C, where C lies to this cardinality of set, minus sigma 1, Okay, this also is the denominator working. So therefore C is again varying over this cardinality set of C. So therefore what does this, what does the first term compute to? It computes to mod x. And what does the second term compute to? Mod y. Mod y, because for each collection you are getting a 1, right? So this computes to mod y. So therefore this is nothing but mod of x minus mod of y divided by mod of x. So now you see that we have actually made one assumption in the theorem which says that mod of x is greater than twice of mod of y. Okay, so if I assume this, and this is quite a practical assumption to make. Okay, so in that case mod of x is greater than twice of mod of y. If I assume this, then this particular thing is greater than half, right? So therefore your probability of success is at least equal to half, right? So you note one thing, that whenever we are doing this kind of reductions, or the reductions that we have discussed in the class, we have assumed the ideal hash function assumption. Okay, we assume that the hash functions are ideal. So basically all these proofs that we have shown are under the random oracle model. Okay, so if the random oracle model is violated, then these proofs or these reductions may not hold true. So we have to be careful. Okay, so what was the ideal hash function model? The main assumption was that if I need to compute a new hash value, how many previous hash values you have computed, if you are computing the hash for a new input, then you have to again compute it. Previous value should not help you, right? Very informally this was the meaning. Okay, so now you can actually ponder upon a point which says that if the oracle preimage has a success probability of epsilon which is less than 1, then what is the minimum probability of success of collision to preimage algorithm? So you can just think on this actually. Okay, so now we go into the construction of iterated hash functions, and we will take up a particular type of construction which is known as the Merkle-Damgard construction. Okay, so the idea is that you have got a compression function. So all these iterated hash functions has got an underlying concept, that is there is a compression function, which means that it takes a large number of values and it compresses to a small output bits. Okay, and using this we will iterate this so that my domain actually becomes infinite and my output is still constant. Okay, so therefore now if you see this slide, extending a compression function to a hash function with an infinite domain. So that is the objective of the iterated algorithm. Okay, so a hash function is created in this fashion, is called an iterated hash function. So we will consider a hash function whose inputs and outputs are bit strings, which means they are 0, 1 values. And again, so you note this, that okay, we know this, that mod x denotes the length of a bit string x, and this particular symbol is a concatenation symbol. Okay, so x concatenated y will be represented in this fashion. So x is a string, y is a string, and we concatenate in this form. Okay, so these are some notations. So now let's start the algorithm. Okay, so therefore the basic concept behind this construction is that you have got a compress function. Okay, so which means that you have got a compress block which will take in, say, an m plus t bits and will give you a 0, 1 m bit output. Okay, so therefore this is a compression function. Okay, so t is typically greater than or equal to 1. Okay, so therefore now what you will do is that your input x can be actually quite large, and using that you are computing the hash value, right? So the first thing which you do is that you have got the input string x, okay, which you can think that this is you can actually break them into blocks. Okay, so what you can do is that you can break them into sub blocks such that each block, okay, is actually divisible by t, so or rather is equal to t. Okay, so therefore you understand that in the last block there can be some values I mean it is not exactly equal to t. So therefore what you do is that you do a padding. Okay, so you extend this and you make it also equal to t. Okay, so this particular step is actually called the pre-processing step. Okay, so therefore what you do is that you take x and you make the output of this particular pre-processing step a multiple of the size of that block, a multiple of t. Okay, so therefore you see that what you do is that you take an input string x where mod x is greater than equal to m plus t plus 1, and the output string y is such that mod of y is actually equal to 0 mod t, which means it is divisible by t, and y you are actually breaking up like y1, y2 and so on till yr. So therefore r, I mean for each block is actually equal to t. So that means r into t should be the cardinality of y. Okay, so cardinality of y means the number of bits which are there in the block y. Okay, so then you have got certain steps. I mean you do an sort of an iterated algorithm. So therefore what you do is that you take one steps, that is you start computing with y. So now you have got this y. So this y has got each of the blocks as size of t, right, and you have got the compress function which takes m plus t bits and gives you m bit output. Okay, so what you do is that now to this compress function, okay, you feed in t bits from y and you feed in m bits. So you start with say something which I called as an IV or an initialization vector. Okay, so now this will result in an m bit output, right. So this m bit output, what I am doing is that I am passing on as my first as some parameter. Okay, so some parameter, which means suppose I can call that as z1. Okay, so next what I do is that I take this m bit and I take the next t bits from y, and again I pass that to my compress function, and I again obtain another m bits. I call that z2. Okay, so similarly I keep on repeating this process. The final compress step which you obtain also will therefore result in an m bit output, right. So this particular output, which is let us write that as zr, because there are r blocks of y. Okay, this zr is sometimes called the hash function output, or zr is often given an optional transformation, like for example gzr, and that is actually called hx. Okay, so g is optional, which means that you can either make it an identity function or you can have a g transformation.
Sir,
yeah,
that m output, that m bit output from the first compress function
yeah,
is also fed to the second one.
this m bit is actually fed to the compress. Yeah. Okay, so therefore this compress now has got an m plus t bits of input, and it also results in an m bit output. Okay, this is the way you keep on iterating this process, right. So therefore this final zr which you obtain, like you are exporting some values like z1, z2 and so on, the rth value, that is zr, is sometimes given an optional transformation, sometimes not. Optional means sometimes you don't give it. So therefore gzr is actually called hx. Okay, so this is the basic idea behind iterated hash functions, and so this is what I have already told to you. So you can go back and look into this slide, but so let us consider a typical pre-processing step. Okay, so therefore what it does is that if you see that you have got y and you have got x, so what you do is that you concatenate it with pad x. Okay, so pad x is nothing but a simple padding function. So it generally has the value of mod x. Okay, and what you do is that you pad it to the left with additional zeros, so that the sum is a multiple of t. So this is a very simple step which I have already told you. Okay, so now you note one thing, that I mean the main thing is that to be noted here is that this pre-processing step has to be an injective function. So what does injective function mean? It has to be a one-to-one transformation. Okay, why? Because if it is not a one-to-one transformation, then I can concentrate on this pre-processing step itself and create a collision, right? So collision creating should be quite easy in that case. So therefore, you have to ensure that the preprocessing step is actually a one-to-one mapping. Okay. So therefore, you note that the preprocessing step has to be injective, and therefore you see that mod of y, that is the number of values in y, is actually equal to RT, which is greater than the value of number of values in x. Okay. So this is necessary for one-to-one transformation, right? This cannot be lesser than mod of x. Okay. So these are some minor points. So now we come into the original Merkle-Damgard construction, and let us concentrate upon this. So this is basically the same iterated hash function technique only, but slightly there are some small minor changes. Okay, so let's concentrate. So what you do is that again you use the complex function, which is an m plus t bit to m bits. So this is a collision resistant, and this is used to construct a collision resistant hash function. So therefore you see that the domain of your hash function is actually an arbitrary size 0,1 string, and from there you are obtaining a 0,1 m bit output. Okay. The main advantage of using, or main elegance of using the Merkle-Damgard construction is that it gives you a wonderful proof. Okay. So the proof idea is like this. So okay, before I go into the proof, I will discuss about the construction, but I'll just give you the idea behind what I mean by the term proof. Okay. So proof means that, so your problem is now to create a hash function which is collision resistant, right? So now there is a quite big problem, because what you are saying is that you will take a very large string and you will compress that into a small m bit string, right, and which has to be still collision resistant. So the beauty of this Merkle-Damgard construction is that it reduces this problem to the collision resistance of the compress function. Okay. So the compress function is a much smaller problem. Now it is just an m plus t bit input which you are compressing into an m bit output. Okay. And it gives you a proof that if you are able to make a compress function which is not collision resistant, or rather which is collision resistant, then your hash function is also collision resistant. Okay. So that is the basic elegance of the Merkle-Damgard construction, right. So now let's go through the steps of the construction before going into the proof. So you see that x is again taken as a k bit value like x1, x2 and so on. So all of them are in this case, all the size of each particular block is actually equal to t minus 1. So it's not t as we saw in the general overview of the construction. Okay. So it is actually equal to t minus 1, and in the last block is actually of size of t minus 1 minus d. So in order to make it t minus 1 size, what do I have to do? I have to add d zeros. Okay. So therefore in this case the size of d has to be lesser than equal to, is actually lesser than equal to t minus 2. Okay. That's the way how you are breaking it. Okay. So therefore what is the value of k? So k will be, in this case you already have your size as n, but if you have padded that with d blocks, it becomes n plus d, right. So therefore n plus d divided by t minus 1 should be the value of k, right, and that you can represent as ceil of n divided by t minus 1, right. So now let us see the construction. Okay. So the construction, you have to go through this algorithm little bit. So you see that 0,1 m plus t bit is 201 m bit is my construction's complex function which we have taken, and here we have assumed that t is actually greater than equal to 2. Okay. But ideally t should be actually greater than equal to 1, but we will be excluding the case t equal to 1 for now. Okay. So we will just consider the case when t is greater than equal to 2. Why? Because if t equal to 1, then this k becomes undefined, right. So therefore we will consider that t is greater than equal to 2 for this case. So you see that n is actually equal to the size of x, and k is equal to n divided by t minus 1 and ceil of that. And what you do is that for each of these steps you keep on doing certain operations. Okay. So what you do is like this, you take, so therefore you see that for I equal to 1 to k minus 1, you take xi and assign that to yi. So that is the preprocessing step. Okay. Only the kth block, what you do is that you take xk and to the right you pad that with d zeros. If you do that, then this also becomes of size t minus 1. Then there is an additional step which is actually called Merkle-Damgard strengthening step. Okay, so therefore this is called MD strengthening. Okay, so what is that MD strengthening step? So what you do is this, that is you take yk plus 1 and in yk plus 1 you write the binary representation of d. So d is some value, na, from 4, 5, 6 something, right? So you write the binary representation of d and you pad to the left with zeros. Okay, because you have to make this also of size t minus 1. So all the y values are of size t minus 1. Okay. So this is the way how you create the y's. Okay. Then what you do is that you start your operation. So what you do? You take the first one. So how many bits are there in y1? T minus 1. So you pad that with m plus 1 zeros. Therefore its size becomes, yeah, m plus t plus 1, because m plus t. It becomes equal to m plus t, because there are there are m plus 1 values here and there are t minus 1 values here. So there are m plus t values here. So that means you can feed it to the complex function. If you feed it to the complex function, it will give you back an m bit value. Call that g1. Okay. So now you continue the iterated process, which means that you take gi, which you have obtained in the previous step, and you know you have also obtained yi plus 1, and in between you keep a 1. Okay. And therefore what is the size of this particular string? M plus t. So again you can feed this into the complex function and obtain an m bit output. Okay. So this you can iterate and you can obtain the corresponding values like g1, g2, g3, so on till gk plus 1. Okay. So therefore this final value of gk plus 1 is actually the hash value. Okay, that is the hx value. So you note that this is sort of a pseudo algorithm way of representing the story, but diagrammatically this will look like this. Okay, so therefore what you do is that you take this value of m and then do an additional padding to the kth block, and then finally you add the length block also, which is the yk plus 1th block in the pseudo algorithm, and then you are taking each m1, m2, m3 and so on, and this is the IV value. You can, in my pseudo algorithm I have taken this to be 0 m plus 1. Okay, but that is a public value anyway. Okay, so then what you do is that you feed it to the complex function, you obtain an m bit output, you take the next t minus 1, but in between you have to add a 1 here also, and you continue to do that to obtain the corresponding hash value. Okay, so all the hash functions like SHA, MD5, MD4, okay, this follows this principle. Okay, so now we come to the slightly little bit more complicated part, but it's quite simple proof, which says that suppose compress 0 1 m plus t to 0 1 m is a collision resistant compressed function, then the function this is actually a collision resisted hash function. Okay, so this is the representation of the collision function. You see that your 0 1 string can actually rise from m plus t plus 1 to infinity, right? The domain can be 0 1, from m plus t plus 1 to infinity, and that you are compressing to an m bit output. Okay, so what you have to prove is that if this compressed function is a collision resistant function, okay, so if then this this is a collision resistant function, then your hash function is also collision resistant. So like the previous day's class, what we have assumed is that you will take a knot in both sides. So therefore we will show that, if we assume that the hash function is not collision resistant, so that means if we assume that there is a collision which we have obtained for the hash function, then we can prove that the compressed function also has a hash function, also has a collision. Okay, so if you can find a collision in the hash function efficiently, so efficiently is again under my definition of efficiency, then you can find a collision in the compression function also efficiently. Okay, so how do we prove this? So let us, in order to prove this, let us go back to my algorithm and concentrate upon certain cases. Okay, so you see that both my algorithms are essentially, I've got y1, say yk plus 1. Okay, so now assume that you have been able to find out a collision for the hash function. Okay, so what does it mean? It means that you have found out two values. Okay, so if you assume that the hash function has a collision. So that means that x and x dash which are not the same, okay, has got hx and hx dash as same, right. You have found out two such values which are like this. So that means now if you concentrate upon say y1, I mean concentrate suppose on x and x dash and concentrate upon the two pre-processed steps of x and x dash, okay. So therefore assume that x results in y and x dash results in y dash, okay. So what is y? Y is suppose y1 to yk plus 1 and y dash is say y1 dash to yl plus 1 dash, okay. So this can be two arbitrary lengths and based upon which we have done this operation, okay. So now assume two cases. Case 1 is when mod of x and mod of x dash mod of t minus 1 are not the same, okay. So which means that if you take mod x and mod x dash mod of t minus 1 are not the same, okay. So this is, you know, that it means that if I take a mod of t minus 1, so there is the final number of values which you are padding. So that is minus d in both the cases, right, minus d1 and minus d and minus d dash maybe. So in this case what I am saying is that d and d dash are not the same, right. So therefore yk plus 1 and yk plus 1 dash or rather yl plus 1 dash are different, okay. So now consider upon the hash output. So what was my hash string which was outputted? What was my corresponding hash value? Hx was equal to g of k plus 1 and hx dash was equal to g of l plus 1, okay. So call that g dash of l plus 1, okay. So if hx and hx dash are the same values, then g of k plus 1 will be equal to g of l plus 1 dash, right. Therefore what does it mean? It means that compress g of k with 1 with yk plus 1 will be equal to compress gl dash 1 yl plus 1 dash, right. So now we know that yk plus 1 and yl plus 1 dash are different. So what does it mean? It means that we have been able to find out two values which are giving you the same compressed outputs, right. So therefore what you are showing is that the compressed function is not collision resistant, okay. So this solves one case, right. What about the other case now? That is, so is this part clear? So the other case is when mod of x and mod of x dash mod of t minus 1 are same, okay. So this actually we can, it will be easy if I break this into two parts. So I call that first part as mod of x. The first case is mod of x is equal to mod of x dash. So which means that what does it imply? It implies that k and l are same values, okay. So now if you observe that what you are saying is g of k plus 1 is equal to g of g dash l plus 1, or rather l will be in this case k itself, right. So g dash of k plus 1. So what does it mean? It means that compress, I call that COMP for brevity. So COMP will be g of k 1 and here we have got y of k plus 1 is equal to COMP g of k plus 1 rather 1 and y of k plus 1 dash. Okay. So here you note that y of k plus 1 and y of k dash k plus 1 dash are the same values, right? So what I mean, if you say that this is not a collision for the compressed function, then definitely g of k and g of k dash should be equal. So therefore g of k and g of k dash must be equal, right? So if that be the case, then again compress, we can continue like this. This becomes g of k minus 1 y of okay. So y of k plus y of k, and that is equal to of compress g of k minus 1 dash, and then you have got a 1 here and yk plus yk dash, right? So this is the idea, right? So now you see that what do you have? So if you are still don't want to force a collision of the complex function, then two things become clear. One is that y of k and y of k dash must be same, right? So therefore if this is not a collision, then this implies that y of k is equal to y of k dash and g of k minus 1 is equal to g of k minus 1 dash, right? So now if I assume that g of k minus 1 and g of k dash minus 1 are not the same, then again I can continue in this fashion, right? So if I continue, and since my lengths are both the same, k and l are same, I will continue till g1 equal to g1 dash, right? And what in each case you will have a result like this, like yk equal to yk dash, and again yk minus 1 equal to yk minus 1 dash, and similarly finally we have y1 equal to y1 dash, right? So what you are saying now is that y and y dash are the same, because for each subpart y is have been same in both the cases. So if y and y dash are the same, because my preprocessing step was an injective transformation, so this implies that x and x dash are the same values. But that contradicts my assumption, right? Because I have assumed that x and x dash are different, right? So therefore you see a contradiction. You follow? So this part is also solved, right? So therefore there must be a collision in the compressed function. Okay, so therefore you are able to show this reduction, right? So therefore what about the other case which you have? The other part, case 2b, is mod of x is not equal to mod of x dash. Okay, so this proof is actually quite similar to the case 2a, except for the fact that you have got g of k plus 1 equal to g of l plus 1 dash, right? So if I assume without loss of generality that l is greater than k, okay, then I can continue in this fashion, and what I will obtain is g of 1 in the final step, g of 1 will be equal to g of l minus k plus 1, okay, dash. So what is g1 and what is g of l minus k plus 1 dash? So if you see your algorithm here, just see your algorithm how it starts. So the first step is that you take 0 m plus 1 and you concatenate it with y1, right? So that is what you are compressing to obtain g1, right? So what you are obtaining is 0 of m plus 1 concatenated with y1, and that is what you are compressing, right? And what about this? This is simple, like you take g of l minus k, concatenate it with y1, and then you have got y of l minus k plus 1 dash, right? So what about now? If you compare these two things, you observe the m plus first bit. Okay, the m plus first bit in this case is what? Y1 is of how many bits? Is of t minus 1 bits. This is of m plus 1 bits. Okay, how many bits are there in g dash l minus k? M bits. So there is 1 bit here. How many bits are there here? T minus 1, right? So now observe the m plus first bit. M plus first bit here is 0, but what about the m plus first bit here? It is 1. So therefore they are definitely different, right? And therefore you have essentially again found out a collision in the compressed function. Okay. So now you see why 1 was used and why 0 m plus 1 plus used there, right? So that you understand from the proof actually, right? So this gives you an idea that actually your collision resistance of your compressed function implies that your iterated hash function is also collision resistant, okay, right. So this is again under the ideal assumptions, okay. So we are again assuming that each hash function is an independent computation, okay. If you find that there are dependencies in the hash function, then all these proof systems will crumble. So now we will just talk about conclude with the case when t equal to 1. Okay, so I think this part is clear to us. Okay, so let us consider the case when t equal to 1. So when t is equal to 1, that means that you will take a compressed function 0 1 m plus 1 to 0 1 m, and this is how you do. So you take x, and the pre-processing step is slightly different. So what you do is that you take 1 1, and after that you take any function f, okay, and I mean not any function, a particular function f, and then apply fx1, fx2 and so on. Okay, so you see that mod x means n means what? How many bits are there? N bits are there. For each of the bit you are computing fx1, fx2 and so on. Okay, so this is how you do the encoding. If the input is 0, then the output is also 0, but if the input is 1, then the output is 0 1. Okay, so do you understand the encoding? So therefore, suppose your input is a string like 0 1 0 1 1 like this, then if you are doing this hash encoding f, okay, then for your 0 you get 0, for your 1 you get 0 1, for your 0 you again get 0, for 1 you get 0 1, for again 1 you get 0 1. So this is the way how you are encoding the input x. Okay, so now you see that in this case you take this value of x and you start encoding this, and the only thing is that the first 2 bits are 1. Okay, so why do you keep these 2 things? 2 things are important again. The encoding is an injective encoding, okay, and the other thing is that there does not exist 2 strings x and x dash which are different such that y of x and y of x dash satisfy this kind of relation. That is, y of x is equal to z, which is any arbitrary string concatenated with y of x dash. You see that this can never happen. So that is, no encoding is a postfix of another encoding. Why? Now because y of x will obviously start with 2 1s, right, and y of x dash will also start with 2 1s, but in this yx 2 1s can never occur in between, right, 2 successive 1s can never occur in between. So therefore this relation will never be satisfied. Do you follow? Do you follow? No. Okay, so what I am saying is that if you take 2 values of x and x dash, there can never be a case where y of x dash and y of x dash satisfies this relation. That is, y of x is, y of x dash is a postfix of another encoding, okay, because of the reason that 2 consecutive ones can never occur in the pre-process step. Okay, then it's quite simple. So therefore you obtain this y1, and then what you do is that you take, so each of them are of 1 bit. So what you do is that you take 0 m bits, and this is of y1 is of 1 bit, so that is m plus 1 bits. You compress, you obtain g1, you continue this process. Okay, so you take gi and concatenate it with yi plus 1. So gi is m bits and yi plus 1 is 1 bit. So this is m plus 1 bit. You engage this compress function which gives you an m bit output from an m plus 1 bit output and obtain an m bit output, and finally you are returning gk as the corresponding hash value. Okay, so now this we can actually also show to be collision resistant, and the proof is quite very simple. I will not go into the details of the proof. You can find out the details from Stinson's book. The reason is that if you again you can divide into two cases. Okay, so you again assume that there is a collision for the hash function, which means that there are two x values, x and x dash, which are distinct and which results in the same hashed outputs. Okay, so now you again assume that x and x dash, the sizes are same or the sizes are different. Okay, so if the sizes are different, then the proof is exactly, if the sizes are same, then the proof is exactly same. If the sizes are same, then again you can assume that gk equal to gl dash, and similarly you can again continue and show that y and y dash will be same, and you can continue in that fashion. Okay, but what about the other case when the sizes are not the same? Okay, so if the sizes are not the same, then you will actually show that, so if the sizes are not the same, which means if I assume that the size in one case is k and the size in another case is l, and they are not the same. Okay, so what you do is that you continue from yk and okay, so you start with gk and gl. Okay, gl dash. So if gk and gl dash are the same, because you are assuming that the hash function collides with for two x values, x and x dash, then gk equal to gl dash means what? Gk equal to gl dash means that correspondingly yk plus 1 will be equal to y of l plus 1 dash. Okay, so similarly you can continue, and finally you will have y1 equal to y of l minus k plus 1 dash. Okay, so now this means that you are violating the postfix assumption, because here you have got one string which is actually the postfix of the other string. So you see that this is a shorter string and this is a bigger string for y's. Do you see that? This is a y string in one case and this is a y string in another case, and this actually forms a post part of this is actually a bigger string, right? So therefore you can, if you consider y dash, you can write y dash as some z which is followed by a y string, right? So therefore this is actually violating my property of the encoding function. Okay, so therefore this cannot happen. So therefore there must be a, so therefore again you are proving a contradiction, showing a contradiction, and this establishes the fact that if the compressed function is collision resistant, then your hash function is also collision resistant. Okay, so this is what the theorem says, and if you put the two theorems together, then now you have actually got t greater than equal to 1, because the previous case was t greater than equal to 2 and this case is equal to t equal to 1. So this is what you have showed, that if the compressed function is a collision resistant compressed function, then so is the hash function. Okay, and you can actually compute the number of times the compress is computed in each of the cases, and this works out as follows. Okay, these are quite simple calculations which you can just check how many times the compressed functions are being engaged. Okay, so this is an assignment for you again. So therefore you see that consider a collision resistant function gx which takes an infinite string and results in a 0 1 n bit output. Okay, consider a hash function hx which is 1 concatenated with x if x is of n bits, otherwise it is 0 concatenated with gx. Okay, so now you see, the question is that you have to discuss about the collision and the pre-image resistance of hx. So you see that since gx is collision resistant, hx is also collision resistant. Okay, but what about the pre-image problem? You see that in one case you have found out that there is a 1 as an output, right? So therefore if I assume that 50% of time you will get 1 and 50% of time you will get 0, if you get 1 concatenated with x, then x is, the inverse is so clear, right? So with a probability of at least 50%, you are able to invert the function hx. So what does it mean? This is not pre-image resistant. But what have we proved? We have proved that collision resistance implies pre-image resistance. So where is the anomaly? So there is a small problem in this particular example from what we have proved in the class. Okay, so you are supposed to justify that. Okay, so next time we will again continue with the hash function, and this is the textbook that we have followed, and this is some paper that I have followed. So this is the main book. You can refer to this textbook. You will find these details there. Okay. So we will again continue with cryptographic hash functions next time.